Time for us to do some practice with problems involving surface area. All right, which means more algebra ahead. And of course, thinking about how do we set our problems up? What goes into our radius? That's the big part of surface area, is understanding that, which comes with practice and doing the work. So do as much as you can on your own. If you're following along with the video, make frequent use of the pause button and try to finish the problem first. And if you get stuck, I'm right there to help you. Just unpause me, and I'll come join you wherever you might be. And together, we can work it out, and we're going to become great. And soon, you won't even need me anymore. I'll miss you, but I'm so happy that you're going to be able to do these problems on your own. But for now, let's begin. Our first problem. Consider the curve y equals e to the 2x, where x goes from 0 to 1. And for each of the following, we're going to set up, but not evaluate an integral. So this is all about setting things up. And what are we going to do? Well, we're going to find an integral with respect to x that finds the surface area. Ooh, surface area problem. In fact, this is, okay, all these are surface areas. When the curve is spun around, y equals -1. Similarly, when we spin around, x equals 2. And then similarly, notice with respect to y, when the curve is spun around, y equals -1. These two are ultimately the same thing, where we're going to find the surface area of the same curve spun around the same line. The only thing that's different is whether we integrate with respect to x or with respect to y. So we'll get a chance to talk about, well, what does it mean to integrate with respect to x, with respect to y, what changes? And similarly, if you look at the second and fourth one, there again, it's the same surface. The question becomes, okay, what are we integrating with respect to, and what's the effect of that have? So let's do a sort of a quick, rough sketch of what we have. So we have our axes here, and we have our curve y equals e to the 2x from 0 to 1. Well, let's just say it looks something like that. It probably not quite that, but it's close enough. So there's 1, and this is at y equals 1 there. Now we should draw our two lines. Y equals -1 and x equals 2. So y equals -1 would be down here. Y equals -1. And on the other hand, x equals 2 would be over here. All right, so now we have our picture of where we're spinning around, our various parts, how it all fits together. And, well, there's a few more things we should make notes of. So, first off, if we have y is equal to e to the 2x, well, that's y as a function of x. So if we were integrating with respect to x, that's great. If we want to integrate with respect to y, we need to write x as a function of y. All right, so we need to somehow do the inverse. Well, that's not so bad. There is, after all, only one x involved. So we say, all right, what do we need to do? We need to get that x out of the exponent. Well, logs are great at that. So we could say log of y is 2x, or we really could say x equals 1/2 log of y. All right, well, that's good. And let's see, anything else we should mark? Well, we need to know where we're going from. For x, it's pretty straightforward because we're told 0 to 1. For y, well, we already said e to the 0 is 1. Now, what happens when we plug in 1? Get e to the 2. So we're going to go e to the 2. So that's the important thing to know. And now, one other thing I want to mark, which is to say, let's think about what we're doing here. What we're doing is, whenever we think about setting up a problem about surface area, we say we're taking a little tiny piece. Well, that's always integrals. Little tiny pieces, right? Little tiny piece. So here, there's our, look at it. It's so little. It's that tiny piece. And then we're going to say, what happens to that tiny piece? So what we need to understand is these distances. Well, let's just write them for right now in a very simple way. if I'm thinking of this point just as the point x comma y, the distance from this y down to y equals -1, well, here we can see that the curve is on top. It's a larger value. High minus low. So this y value, subtract the y value down here, y minus -1 means that this length is y plus 1. And over here, when we think about going from our point xy that we're spinning over to 2, well, okay, now the 2 is the larger value. It's right minus left, high minus low. So this length would be 2 minus x. All right, with all these pieces in place, the rest of the problem will not be so bad. We just need to remind ourselves that our generic formula for surface area, and once we have that, we can almost write down the answer with almost no more work. 2 pi radius and length. So let's start going through them one at a time. We'll start with A. So for A, what do? Well, we know we're going with respect to x. So everything is with respect to x, which means our bounds are with respect to x, and the x bounds go from 0 to 1. In fact, it was given to us from 0 to 1. So we have the integral 0 to 1. We have our 2 pi. Okay. Now comes the radius. And to understand the radius, we have to know where we're spinning. We're spinning around the line y equals -1. So our radius would be y plus 1, but wait, everything has to be in terms of x, so we don't write y plus 1, we replace y by e to the 2x. So e to the 2x plus 1. So this is y plus 1. Okay, that's our radius. And then our length, so remember our length, that's our square root 1 plus our derivative, dy dx, or dy dx squared dx. Or dy, again, you can swap symbols around. So square root of 1 plus, now take the derivative of e to the 2x. Well, that's not so bad. Derivative of e to the 2x, the 2 comes down, and so it'll be 2e to the 2x squared. And we'll just leave it like that. If we really want to, we could write that as 4e to the 4x, but we're satisfied with what we have here. And then dx. And we're done. See, it's not so bad because we're all about the setup. It's all about the setup, No troubles. No troubles. Now, for part B, again, it's with respect to x, so our bounds, 0 to 1, the 2 pi is the 2 pi. We come to the radius. So we're going around x equals 2, so the radius would be 2 minus x. Well, we're integrating with respect to x. Perfect. 2 minus x, we like it as is. No need to do anything fancy, so we just write in 2 minus x. The length part is exactly the same. So we can just copy it from the previous line. So square root of 1 plus 2e to the 2x, quantity squared dx. All right, good. Now on to our next one, right? Let's see, which is part C. With respect to y. Okay, now we're shifting gears. So for part C, we should use, since we're integrating with respect to y, we have to have our bounds in terms of y. We say, well, the curve goes from 1 to e squared. So that's our bounds. 1 to e squared. 2 pi. Where are we spinning around? That determines our r. Well, it's around y equals -1, which would be this y plus 1. So now this becomes y plus 1. And then the square root of, well, what's next? Well, it's 1 plus, and then we come here and say, what's the derivative of x with respect to y? Well, the derivative of 1/2 times log y is 1/2 times 1 over y. The derivative of log of y would be 1 over y. So we would have 1 over 2y quantity squared. and dy. There you go. Good. Now, that leaves us with just one more. One more to do. All right, so part D. So this is, again, with respect to y. So same bounds with respect to y. 1 to e squared, 2 pi. Now, we're going on x equals 2. So it should be 2 minus x. Well, I can't have it as 2 minus x. I need everything in terms of y. So what to do? Well, we replace x by what it is. X is 1/2 log y. So this is 2 minus 1/2 natural log of y. And then the rest of it is the same. In other words, it's the square root of 1 plus, take the derivative, 1 over 2y squared dy. Good. Done. That's it. Because we've now set all of them up. And if you were able to do the integrals again, a and c represent the same surface, and therefore they'd have equal value. And similarly, b and d, same surface, they'll have equal value as well. All right, good. Well, that's sort of a nice idea that says, hey, we can set things up. We can also, instead of integrating with respect to x, we can change it with respect to y, and just think about what changes when you go through and carry out that process. All right. Well, on to some more problems. We need more practice, and the more practice we get, the better we'll become. Find the surface area when the curve y equals 2/3 times x squared plus 1 to the 3/2, and x here goes from 0 to 1, is rotated around the y-axis. Now this curve, x squared plus 1 to the 3/2, I don't know exactly what it looks like, but I can imagine. I know when I plug in 0, I can see, it's 0 plus 1 to the 3/2. Okay, that's 1 to the 3/2. It's 2/3, and as x gets bigger, the term gets bigger. All right, so at the very least, we can get a vague sense of the shape. It's going to do something along the lines of the following, where we start at about 2/3, and then we go up. Okay, so we'll just give ourselves a picture here. It's not the most accurate picture, but it doesn't have to be accurate. We're really working on intuition. So here we go. There's our 1, and we're spinning around the y-axis, and that's important. You got to keep track of where you spin. All right. So we think to ourselves, let's think about a little tiny piece. So there's our little tiny piece, and we're going to spin it. And so we say, well, what's the distance? Well, first off, what are we going to integrate with respect to? Well, everything so far has been given us in terms of x. X goes from 0 to 1. Y is a function of x. And so we really should think of things in terms of x. So the distance would be x. That's how far it is to the y-axis. So our surface area, our generic formula, adding up, which really is just another way to say integrate, a to b, our 2 pi, times our radius, and times our length. Where our radius, in our case, would be x, our a and our b would be 0 and 1, and our length, well, that's the square root of 1 plus f prime of x squared dx. This is probably where we should spend a little bit of time. I suspect if we can get a handle on that part, the rest of it won't be so bad. So let's do a little bit of scratch work on the side. So we have the following. So the square root of 1 plus f prime of x squared, well, that's the square root of 1 plus, now let's work it out here. We have the 2/3. Then we take the derivative, the 3/2 comes down, so times 3/2. And then we have x squared plus 1 to the 1/2. And then, of course, chain rule, there's a 2x. And then that whole expression is being squared. Okay, that's not so bad. We say, well, some cancellation, the 3's and the 2's. Woohoo! That's good. Probably what's going to happen anyways. We oftentimes suspect, hey, nice things should happen, especially when we're nice people. We're careful with our algebra. Good things should happen to us. So that's going to become the square root of 1 plus. Now, when you square this to the 1/2 to the 2, x squared plus 1. Then here, you'll get 2 squared and x squared. So 4x squared. So that becomes what? Square root. Well, let's put things in the highest power first. So the highest power would be that when the x squared and x squared get multiplied. So that would be 4x to the 4th. Then here, 1 times 4x squared, 4x squared, and then a 1 on the end. Now, what do we hope for? Well, it would be great if this were a perfect square. And oftentimes when we see sort of 3 terms, we're like, maybe this is a perfect square. Maybe. What would it be? Well, we'd have to have the a squared and the b squared beginning at the end, and then the middle would be a 2ab. Well, what does that tell us? Well, we'd have to have a 1 squared on the end. Here, it would be a 2x squared squared at the beginning. So the question is, if I multiply 2 times 2x squared times 1, do I end up with 4x squared? And the answer is yes, we do. We do. Ha ha ha! It's a perfect square. This is fantastic. It's a great way for us to get rid of our square roots. So we have, this is really the square root of a plus b squared, or if you like, 2x squared plus 1. So that, that says this expression right here is becoming 2x squared plus 1. Ah, good, good. So let's update. So what do we have? That says that our surface area becomes, let me switch colors since we're now on a sort of a new line of thought. Putting everything together, we have integral 0 to 1. And then we have our 2 pi x 2x squared plus 1 dx. Well, 2 pi can come out. Integral 0 to 1. And then you can multiply the x through. So that's 2x cubed plus x dx. Now we're ready to go. We integrate. So this would be what? 2 pi. And then when we integrate, add 1. So that would be x to the 4th. And then divide by 4. 2 over 4 is a half. Plus, here, x squared, divide by 2, a half, x squared. And evaluate from 0 to 1. Well, when you plug in 0, you get 0. When you plug in 1, you get a half plus a half. Half plus a half gets us to 1. And therefore, our final answer is very nice, very short. It's 2 pi. 2 pi. There we go. Good. Good. Wonderful. Woohoo! Nice problem. Nice answer. Nice answer. All right. Well, let's try another problem. Okay. So, let R be the region enclosed by the function x squared and the function 4 minus 2x minus x squared. And suppose we spin this around the x-axis. The problem is set up, but do not evaluate the integrals needed to find the surface area of this solid of revolution. So, in other words, we have this sort of unusual shape here. What is our unusual shape? Well, we know some of it. We have the x squared. Okay, that's not that unusual, x squared. And so what is that? That's our parabola. And then we have this other parabola, 4 minus 2x minus x squared. Well, maybe it's not so clear what that parabola is, but there's a couple of hints. We see the minus, which really tells us it's a downward parabola. And so we also see the intercept is at 4. So we can imagine it's 4. It's probably going to look something like that, vaguely speaking. So what do we have? Well, our region is this sort of inside blob. So that's R. This is R. And what are we going to do with it? Well, we're going to spin it around the axis. And we're in particular here around the x-axis. And now the question becomes, all right, what happens to the surface area? So we can think of it really as being two parts. We have what happens to the surface area when we spin this bottom part. What's the surface area when we spin this top part? So it's perfectly fine to think about, well, if I'm after surface area, let me break it into pieces where each piece is reasonable to work with. So what do we do here? Well, we have a lot of our pieces in place, but what we need to do is figure out where we start and stop. Right now, everything's in terms of x. Let's keep everything in terms of x. So we want to find these locations. Where do we start and stop? Well, that would happen when 4 minus 2x minus x squared were equal to x squared. If we move everything over, that would say that 0 would be equal to 2x squared plus 2x minus 4. Well, if you can factor out a 2, so that's x squared plus x minus 2. And not too surprising, as our problems often do, it factors in a nice way. So x squared plus x minus 2 can factor as what? Well, I need two things multiplying together to give negative 2, adding together to give 1. X plus 2, x minus 1. That'll do it, right? We can check. X squared, good. Minus x plus 2x, perfect, x. And then minus 2. So that tells us what? Well, it tells us, see, because of this 0, either x plus 2 equals 0, which gives us negative 2, or x minus 1 equals 0, which gives us positive 1. Good, good. Now we know where we start and where we stop. We also know we're after surface area. And how do we know that? Well, not just because today is surface area practice day, but because it says surface area. And so we remember the basic formula. Surface area is you're adding up from A to B of 2 pi radius and length. Okay, and now with this in mind, we're ready to do our answer. Isn't it great? It feels like we're ready to finish. It feels like we've only started. Well, once you know what you're doing, oftentimes it's just a matter of putting everything together. And most of our pieces now are on the board. So our answer, well, our surface area, we're going to do it in two parts. This bottom part, what's that surface area? This top part, what's that surface area? Add them up, that's our total. So let's do our bottom part. So we're just going to go from negative 2 to 1, our 2 pi. Now, our radius, well, that's going to be from the curve, which is y equals x squared, down to the axis. Well, that's y equals 0. So it's the function. The function is our radius. So 2 pi x squared, then it'll be the square root of 1 plus. Now we take the derivative of our function. The derivative of x squared is 2x squared dx. So this is the bottom portion. Then we're going to add to that the top portion. Well, same x bounds, negative 2 to 1. 2 pi is always there. Now, on the top, we're going to go from this curve, 4 minus 2x minus x squared, down to the axis. Well, the distance there is the function. Again, it's not surprising. So it's 4 minus 2x minus x squared. Square root of 1 plus. Now it's our derivative. So minus 2 minus 2x squared and dx. 2 pi radius length. 2 pi radius length. There's our bottom. There's our top. And now we've set it up. And that's all we were asked to do. So we're done. We're done. We found it. Good. That's not so bad. Break things into parts. It's a great way to approach problem solving. is saying, look, instead of trying to do it all at once, let's break things into individual pieces, and then we'll work each part and then put it all back together. It's really the philosophy of integration. Break things into small parts, figure out each part, put it back together. So it's a beautiful idea. Beautiful idea. Okay, good. Woo. On to another problem. Well, what's this one going to be? Find the surface area when y equals x cubed, where x goes between 0 and 1 over the 4th root of 3. Okay. Well, is spun around the x-axis. Well, let's see where we go. And should be interesting. So what do we have? So our basic picture, x cubed, we know what x cubed looks like. So we're going to be going up, and here's 0, and we'll say this is 1 over the 4th root of 3. A suspicious number. Well, sometimes suspicious numbers are there for a good reason, because what might happen is that once we evaluate, things become really clean. It's a bad number at the beginning can be a sign that it'll become a good number later on. Don't judge a book by its cover. Don't give up on a problem right away. Work it. See what happens. Oftentimes, things aren't as bad as they seem. Okay, so here we go. What can we say? Well, our basic surface area problem, surface area, is we're going to add up our little pieces, 2 pi, our radius, and our length. Okay, well that's not surprising. That probably sounds really familiar by now. We've been using that formula quite a lot. Everything is given in terms of x. We're going to integrate with respect to x. And our function is pretty easy. So the only thing that we really have to focus on is saying, well, what's the radius? So you think of taking a little tiny piece, and you ask, well, how far is it down to where we're spinning? Well, in our case, we're spinning on the x-axis. So our distance here would be y, which is really going to become x cubed. So for us, we get that our surface area, we're adding up 0 to this number, 1 over the 4th root of 3. I know it's hard to read, that says the 4th root. 2 pi, our radius, x cubed. Then our length, that's our square root, 1 plus function, take the derivative of that. And so that's 3x squared dx. And there we go. Okay, well, let's clean it up a little bit. I mean, not much we can really do here. So what do we have? We have 0, 1 over the 4th root of 3, 2 pi x cubed square root 1 plus 9x to the 4th. Okay, well, that's something we do. We can square the inside. And now we look at this and say, well, oh, wait, there's a 4th degree here, right? X to the 4th. That's a 3rd degree, x cubed. Perfect. This is setting ourselves up for something nice to happen. Because when I take the derivative of x to the 4th, I get something that looks like x to the 3rd. So what we should do is say, look, that tells us there's a good substitution to make. The inside, well, substitution often is an inside job. So u equals 1 plus 9x to the 4th. Then we could say that du, well, is 36x to the 3rd, because we're bringing the 4 down, dx. Well, there's not really a 36 there, so we'll just move that to the other side, 1 over 36. There we go. All right, so what do we get? Well, we get that this is equal to the integral. We'll come back and do the bounds in a second. 2 pi will still be there. The x cubed dx, well, x cubed dx becomes 1 over 36 du. And then we have this square root of 1 plus 9x to the 4th. Well, that becomes square root of u, or, if you like, u to the 1/2. You probably are thinking, This seems to be happening a lot where there's a substitution, we end up with the square root of u. Well, yeah, that's oftentimes how we deal with square roots, is find a way so that the inside somehow collapses, becomes a square, or there's a substitution. It's not so surprising that we see these in these types of problems. We're not done with the change. We still have to worry about the bounds. These bounds are x bounds, and we know they're x bounds because we're integrating dx. So that really says that this is x equals 0. X equals 1 over the 4th root of 3. So now, let's switch to u bounds. So we plug in x equals 0. Well, that's easy. 0 to the 4th is 0, so we end up with 1. Now, let's see if this crazy number is going to be nice to us. The 4th root of 3. Well, we take that to the 4th power. The 4th root and the 4th power undo each other. So what happens is that x to the 4th becomes 1/3. 1/3 times 9 becomes 3, and 3 plus 1 becomes 4. So it's the integral from 1 to 4. Nice. Good. It came out a little clean in the end, which is good. We like it when it does that. We can simplify a tiny bit here. There's a 2 and a 36, so we can knock up a little bit down here. So that's 1 over 18 now. So we end up with pi over 18. And now we integrate u to the 1/2. That would be u to the 3/2, and then multiplied by the reciprocal 2/3. And we're going to evaluate 1 to 4. All right, well, we can do some more cancellation. There's another 2, and there's an 18, so that's now a 9. So we are up to saying that this is pi over 27. Then we have 4 to the 3/2. Well, square root of 4 is 2. 2 cubed is 8. Now subtract 1 to the 3/2. Well, 1 to the 3/2 would be 1. So 8 subtract 1, and that's going to be 7. So we end up with 7 27ths pi. And there you go. That's the answer. That's it. Beautiful. It worked out kind of nice in the end. And so if we had this weird number, we'd have a weird answer. And so, it was almost kind of a trade-off. It's like something has to be weird somewhere. Do we want it to be weird at the start or weird at the end? But you know what? I like a beautiful answer. And so that's why I'm saying, look, I'm willing to be weird at the start if I have something beautiful at the end. Because life is beautiful. We should enjoy having beautiful answers. All right, good. Well, let's do another problem. All right. So, set up, but do not evaluate. Aha, we've been doing that a lot. Well, because it turns out these are hard to evaluate. In integral, to find the surface area when y equals e to the x for 0 less than or equal to x less than or equal to 1 is spun around the line, wait, what? Y equals x? What? We're not spinning it around an axis? What? Oh my goodness, wow. This is crazy. Okay. Oh my God. Okay, let's get a picture here so we understand what this question is asking. So we have our curve, y equals e to the x. All right, well, that's not so bad. We're familiar with that. Okay, so here we go, e to the x, and we'll just say it does something like that. And now it says we're spinning, but we're not spinning around some horizontal line. We're not spinning around some vertical line. What's going to end up happening is we're spinning around this sort of diagonal line, y equals x. So we're going to go and spin it this way. So here's this line, y equals x. That's so strange. And so what's our shape going to end up becoming? Well, we can kind of get a rough sketch here. Let's see. We'll grab, and our shape is going to become something like that. So there we go. That's what we're after, that surface area. Now, our initial thought is this even possible? Do we have the technology that would allow us to do this problem? It's not so clear that the answer is yes. But we should see. So one of the nice things here is the flexibility of saying, what is the integral that we're working with? So if you think about our formula, what do we have? Well, it's 2 pi, and we're adding up. Should have started with that. And then there's a radius, and then there's a length, where the length is a piece of the curve. So what changes when we change what line we spin around? So what changes if a line here versus a line there, or a line here, or a line there, or maybe even a line here? Well, let's think about what doesn't change. The parts that don't change are the length, this integral from A to B. So what we really have to do is spend our energy on this part. So that's what changes. So it doesn't matter that it's not a flat line that's horizontal or a flat line that's vertical. Any line can work as long as we understand what the radius is. So we come to our little tiny piece, because we always think about taking a little piece. So there's my little piece. And what we're going to do is come here and ask the question, how far is that distance? This is our radius. And once we understand that, then the problem is not so bad. Now, I didn't finish reading the problem because I got so sort of a bit flummoxed by what the problem was asking, I forgot to read this last part. There's this comment. The distance from the point AB, so I can think of this as the point here as AB, to the line y equals x is 1 over root 2 times absolute value of a minus b. Okay, so that radius is being represented there. Now we have to rewrite this in terms of our variable. Everything so far has been given us as x. Y equals x, x bounds 0 to 1. So let's think of it in terms of x. So this point, AB, really should be thought of as point x comma e to the x. So for us, our distance would be 1 over root 2, and then a would be x, and then b would be e to the x, a minus b. Now, let's go ahead and we have two options. We can leave it as the absolute value, or we could say, could we get rid of the absolute value? We could if we could figure out which one is bigger. So if I'm over here, is my x value bigger or is my y value bigger? Well, let's just pick on this point. It doesn't matter which point we pick on. They're all going to be the same because we're all on one side of y equals x. So notice, is my x value bigger or y value bigger here? Well, it's the y. X equals 0, y equals 1. So actually, x minus e to the x is a negative quantity. So for us, we could say our distance is 1 over root 2 e to the x minus x. So this is the radius. Now, we're basically done. We know where we're going from, 0 to 1. So integral 0 to 1. 2 pi, don't forget that. That's important. And then our distance, our radius to where we're spinning, is this expression. 1 over root 2 e to the x minus x. Finally, our length. It's the same length as before, because the length isn't dependent upon where we spin. It's just saying what's the length of the piece. So that's our same basic formula, square root 1 plus. Now we have to think about what's the derivative of e to the x. Well, we probably don't have to think hard. The derivative of e to the x is e to the x, and then we square it. And we're done. That's the answer. Now we can do some things like clean it up. For example, the 2 over root 2, we could simplify that. And we could write that if we wanted to as root 2 times pi. Then, of course, e to the x minus x. And if I have e to the x squared, that's really 1 plus e to the 2x dx. So that's another way to write the answer. And this is an integral we definitely don't want to be doing. That would be a terrible integral to try to find an antiderivative for, because I don't think we could, even if we tried for a very long time, and even though we're both very smart. But that's okay. We can always get good numerical approximations. But for now, we're just happy. We set it up our problem. And the moral here is it's better to understand what the pieces represent than to memorize formulas. If you say, oh, I know how to memorize the formula around the x-axis, I know how to memorize the formula around the y-axis, and then I just plug it in. Well, what if we switch it to a different line? Then you're like, I have to memorize another formula? But if you say, oh, wait a second, I just have to think about radius, then it doesn't matter, x-axis, y-axis, any other line, I know what that piece represents. I just have to figure out what does it represent for this particular problem. Okay, so there we go. Good. Well, let's try one more. One last problem to finish it up. Set up, but do not evaluate. Another set up, but do not evaluate problem. Okay, an integral which gives the surface area when y equals 25 minus x squared, where we go from negative 5 to positive 5, is spun around the line y equals 16. Okay, well, what is going on here? Why did they save this one for the last? Is there something here that is perhaps going to be a little bit bamboozling? I don't know. Why is this one the last one? Because usually don't they save the best for last? I think that's a good philosophy. Okay, so what do we have? Well, 25 minus x squared, that's not so hard. That's an upside down parabola. In fact, that one we can pretty much draw without any problems at all. Intercepts at negative 5 and positive 5, and comes up and comes down. And over here is 25. Where are we spinning it around? Well, we're spinning it around y equals 16, which is right here. And at this point, you have one of two reactions, like, meh, or, what? Is that allowed? Now, what might be the is that allowed camp? What might they complain about? Well, somehow the line that we're spinning around, this line y equals 16, is going straight through the curve. And the question, is this allowed? Is, well, yeah, you can do it. It's perfectly fine. Nothing weird. What happens is you can really think of this as being sort of a sequence of shapes where you have sort of a central shape here where it, just sort of comes to zoom. That's our central shape. And then you have on the side these other two sort of ear type shapes coming through. So it's kind of vaguely reminiscent of a TIE fighter. If you ever seen the TIE fighters where you have that big pot in the middle and the two things on the side. So absolutely, we can get this shape. Now, where's the difficulty? Nothing seems too hard. Well, let's think about the process, right? So our surface area would be the adding up, or if you like, integral a to b, 2 pi, then our radius, and then our length. So, well, let's just write down what we think it should be. Negative 5 to 5, 2 pi. We'll come back to radius. That's almost always the interesting part of these problems, is making sure we understand that. But what about the length? Well, that's actually pretty straightforward. That would be the square root of, if we think of our function here as 25 minus x squared, and I probably should have said this explicitly, we're integrating with respect to x because everything is given in terms of x. Then our derivative, well, that's a very straightforward function too. That's negative 2x. So if I square that, that would be 4x squared. So that would be a 4x squared. It goes here. And then we have a dx, which leaves us with this part here. We have to think about what is our radius. So what is it? Well, here we go. we can just think of it. Well, let me grab a different color so we can spot what's going on. I have to go from y equals 16 to the curve. This will be the radius, right? So, well, what can we do? Well, we take 16, because that's the high value, right? And we subtract 25 minus x squared. Well, 16 minus 25 would be negative 9. Minus x squared would be plus x squared. Or if you like, that's x squared minus 9. And so, now you're like, well, that was easy. We're done, right? But be careful. What's true about radius? Radius is a measurement. It's a distance. If we have a measurement, what needs to be true about that measurement? It always needs to be positive. Notice that y equals 16 compared to the curve. Here, the 16 was on top, curve was on the bottom. If I move a little bit, it switches. So what happens is that x squared minus 9, which before was positive, now all of a sudden is negative. So if we just put x squared minus 9 in for our radius, what ends up happening is that we'll get a positive part from these two ears and a negative part from the center. And so we might end up with an answer, and we might be saying, oh, it might even be positive. I don't know whether this integral that we have written down would be positive or negative. But it wouldn't be the right answer because you get cancellation. It's not supposed to be add the two ears, subtract the middle. It's add the two ears, add the middle. So how do we solve this problem? There's two things you can do. And if you're just doing a setup and that's all you care about, the easiest thing to say is, look, I can always hedge my bet and say, whenever I'm talking about radius, I want to make sure it's a positive value, and therefore put in an absolute value sign. The absolute value guarantees it's a positive quantity, and now it doesn't matter which piece I'm in. I'm always going to be positive, and life is good. Now, if you had to actually integrate this, what would you do? Well, what you would do is say, look, I don't want to do anything with an absolute value, so I'm going to break it up into pieces and say, in this part, the absolute value does nothing, so I can drop it. In this part, the absolute value changes the sign. Okay, we flip the signs on the inside and get rid of the absolute value, and so forth and so on for each piece. So look at what you're spinning. If what you're spinning crosses through the line that you spin around, you don't just want to say, oh, here's r of x and be done with it. You want to say, whoa, let me be careful. I want to make sure I'm always having a positive r of x. In other words, a positive radius, so that I don't get some weird cancellation and I don't get the wrong answer. After all, we like getting correct answers. So that's why this one is here. It's sort of like, be careful. Be careful what you think about. Make sure you understand things should be positive when they should be positive. And that's it. We're done. That's the answer. That's also our last problem. So wonderful set of problems. Great time. Thanks for coming along and doing these problems. The more you do, the better you get. And so keep doing it. You're going to be amazing. You're going to be amazing. All right. Have a great day.